I wanted to set up a problem that is kind of near and dear to my heart. It's something I've been thinking about for far too long, and to be like kind of honest, like, I didn't really do any applied math ever, and I got to graduate school, and I was doing a first kind of project during my PhD where we were making these like little structures that you would compress them, and we would get these little tiny patterns to form on the surface. And so the simplest one I made was a pattern of little arches, and you end up with a shape that looks like this. And I didn't know anything. I came from like a chemistry background, and I was in a materials science department, and so there wasn't a ton of a framework for kind of encountering these problems. And so I was sitting down like, what's the shape of this curve? Like, it should be pretty simple. It looks kind of like a bump. Like, how do we find what the shape of this thing is? And I basically banged my head against the wall for quite a while to, you know, with all the wrong tools and all the wrong approaches and looking in all the wrong places to figure out, you know, what is the equation that describes this shape. And so I kind of wanted to show you, this shape is really important. Like, it seems kind of silly, but this shape is immensely important. And the development, kind of understanding the shape and being able to predict this shape. For one thing, trying to predict this shape is actually what led to the development of a lot of the mathematics that we're talking about here. It led to a lot of mathematical developments in terms of theories of elliptic integrals and elliptic curves. The shape here has been used from everything to used in everything from trying to computationally model hair in Disney animations, to describing the shape of DNA, to creating the splines that are used by shipbuilders to create the form of a ship, to, if you've ever used Adobe Illustrator, there's a paintbrush tool in Adobe Illustrator. And what's remarkable about this paintbrush tool in Adobe Illustrator is that it actually models the bristles of a brush as these thin rods. And so when you do this, it's modeling what the brush fibers would be doing by solving these equations. And it also presents us in this class a really nice way to apply our variational approach to derive the equations for this. But then also, like we were talking about last class, one of the benefits of the variational approach to deriving the governing equations is that you get some of the boundary conditions for free. And so I thought this would be a good example for us to derive the governing equation of this curve. This curve is known as the Elastica. And along the way, kind of retain the boundary terms, so that we can see how those terms that kind of we've been throwing away and saying, oh, this is zero. Actually, if we just kind of keep them and look at them, they instruct us on what some of the boundary conditions actually are for solving this equation. So I thought this would be kind of useful. And I would like this to be a class where I send you off into breakout rooms to work through this. But before that, assuming none of you know anything about elasticity, which may not be true, but it's probably a safe assumption for the class in general, I want to get you to the point where we can start this problem. So I'm going to set the table by kind of arriving at the Lagrangian that we need to minimize. I'm going to ask you to minimize it by not using the Euler-Lagrange equations. What I want you to do is kind of start with the variational approach, which is perturb the quantity, do your integration by parts, kind of get rid of the terms that need to vanish, arrive at your governing equations, and then look at and think about the terms that kind of emerge through that integration by parts, describing what's happening at the boundary. So assuming you don't know anything about elasticity, let me give you a little crash course in how do we find the Lagrangian for this problem. So let me sketch out what we're talking about. And the simplest way to do this would be reduce the problem I just showed you. I'm not sharing this, am I? Let me share this real quick. Come on. There we go. So that's our one-dimensional beam. It's on some pins. We don't really even have to think about anything specific about what it's resting on yet. We can just kind of imagine that it's a bar. It's in 1D, just has it's like a line. And what we're going to do is take one of the ends of this bar, pretend it's on a roller, and just kind of slide it to the left a little bit. And we'll know that we're going to have some curve like that appearing. That's going to be in response to, obviously, we have to have pushed on this thing with some amount. So we'll have a force P that we're pushing on there. One of the things that we'll get into towards the very end of this course is ideas from differential geometry. And one of the kind of simplest ways to appreciate why differential geometry can be useful is that as you've kind of encountered throughout your career, sometimes it's easier to solve problems in different coordinate systems. So you're used to doing things in Cartesian coordinates. You're probably also familiar with cylindrical or polar coordinates, and you might have done one or two things in spherical coordinates, maybe in like a multivariate calculus course along the way, or maybe if you studied droplets or something. Oftentimes, when you're dealing with large deformations of elastic objects, it's better to live on the coordinates of the object itself. And so in this case, what does that mean? It means that, we could, do everything in terms of X and Y, but, as you look at the structure, what on earth does X and Y mean when you have something like this? Extremely, extremely large deformations. The Cartesian approximation works really well if you're assuming small slopes. If you're assuming that like this thing is really deformed like this. Let's see, like that, say. And that's what you do in mechanics of materials. You derive the equation of the elastic curve. But what we don't tell you is that you derive the equation of the elastic curve entirely in Cartesian coordinates because we're assuming small slopes. We do tell you we're assuming small slopes, but the consequence of assuming small slopes is that you're living in a Cartesian coordinate system. You're not really following the coordinates that apply to the material. It's actually much more useful if we kind of parameterize our problem such that we're kind of living on the coordinates of the object. So what that means is we'll have a new coordinate system. We'll call it S. And you can think of S as like saying, if I give you an S from, say, 0, let's see here. Oops, I can't use orange. Pink here. So we'll say this bar has a length L. And so I still have the ability to tell you S from anywhere from 0 to L. And it's what it's going to tell you is if I give you a specific S, then you're going to kind of come and say, oh, it's this thing here. And I'm living on the curve. I'm not talking about like where that thing projects down or projects outward. I'm saying S is a point on the curve. Okay, so we pushed on this object, which led to a displacement. And hopefully you remember from Intro to Physics that we've done some work, right? We've applied a force, we've caused a displacement, force times displacement is going to give us work. So we talked about the Lagrangian being the quantity that we want to minimize. And the Lagrangian is the kinetic energy minus the potential energy. One of the things that helps simplify problems in elasticity and in structural mechanics in general is to just first do things as if everything is static and not concern ourselves with any kinetic energy. And so what that means is that we can throw away this term here, and we just have to investigate what the potential energy is. So the potential energy of an elastic structure is the strain energy minus the work being done to it. So strain energy might be a term that's not familiar to you, and really what it's saying is kind of how much energy are we storing in the elastic body because we've deformed it. It's in the case of a really simple classical physics approach, that strain energy refers to the energy you store in a spring. So it's going to be like 1/2 kx squared. You take the derivative of that with respect to x, and you get Hooke's law, F equals kx. In the case of an elastic structure, that's a little bit more complicated. And so let's dig in here. So let's first look at the strain energy term. Strain energy is usually given by the letter U. And in general, it is written as 1/2 the integral over the volume being the volume of the elastic material. And what you're integrating is the product of stress times strain over dV. Now, we can assume that we have small enough strains that our material is behaving in a linearly elastic manner. And so we can use Hooke's law to tell us something about stress. Now, this is something that I think trips people up, because you see this and you say, like, wait a minute, how on earth is that small strain? So I have this massive deformation here. And what I want to emphasize is that there is a difference between small strain and small slopes. And both of those are approximations that can help us at various times. Here, really, there's not much deformation in this elastic body until you get to about maybe like here, where you start to feel kind of the resistance in that bent bar. But doing this really takes very little energy. It's almost like a soft mode, like I could just kind of barely apply any load to it and I get this large deformation. So in this case here, we're not really straining the material. How do we know that? Well, you've all probably taken like a piece of plastic wrap, or maybe a piece of aluminum foil is a better example. You could do this with aluminum foil. You could cut a strip of aluminum foil and do this and come back, and it'll stay flat if you're careful. And we all know that aluminum foil is so easy to plastically deform. Like, you just twist it a little bit and you get creases everywhere. Those are plastic deformations that you're not going to get those recovering back to their initial state. But if you're careful, you take that aluminum foil, you cut a little strip out of it, you compress it a little bit, it'll go back and forth, and it won't leave any permanent deformation in that aluminum foil. And that's indicating to you that you have a material that's so easy to plastically deform, yet you're doing this large deformation and you don't really crease it at all. That must tell you that you're really not imparting much strain on the material. Otherwise, you would have expected it to fold or crease or leave a mark. So we're going to assume that it'd be fair for us to assume this material is linearly elastic, which means we can just use Hooke's law as a way to give us some replacement here, or understanding for what how stress relates to strain. So this is, hold on. And I'm going to use a different epsilon, the more curvy, bendy kind of epsilon there, to make it clear that I'm not talking about epsilon as a small parameter, but epsilon as a tensor that describes deformations in the body. So this is not the same epsilon. Okay, so with a little bit of algebra and replacing, we solve for epsilon and stick sigma over E into here for epsilon. Then we can rewrite this as 1/2 over the volume, which would be stress squared over E times dV. You might also remember from mechanics of materials that we know something about the stress in an object when we bend it. And we know that the stress in the object when we bend it is proportional to the moment we're applying times where we are through the thickness of the object over the second moment of area. So dust off the cobwebs, and this should be something like, in bending, my over I. Now I skipped a step here that it's going to be really important for us to consider in a moment. But because we're saying these strains are small, like these in-plane stretching strains are small, what we're really saying is that even though the deformation of this object, the total strain energy, is going to be the sum of the energy it costs to stretch this thing, the energy it costs to bend this thing, the energy it costs to twist this thing, we're saying, well, we're not twisting it, so we can ignore that. And by making this assumption that we're not really imparting much uniaxial strain to it, so that we're not going to get into that plastic regime, we're going to also say that we're not really stretching the object much. We're just bending it. It's actually a pretty good assumption, and this is true for most things that are thin. Most things that are thin, you can compare the energy that it takes to bend it versus the energy that it takes to stretch it. And with a little bit of algebra, what you'll find is that the energy it takes to bend it scales with the thickness of the object cubed, while the energy it takes to stretch it scales with the thickness. So if you give something that's really, really thin, the energy to bend it is super small compared to the energy to stretch it. And we know, based on the principle of least action, principle of minimum potential energy, that things are going to take the path of least resistance. And things are going to bend if it's cheaper to bend than it is to stretch. And so we're going to, even though the strain energy could consist of stresses from stretching, bending, twisting, transverse shear, we're going to ignore all those except for bending and say, really, this object is just bending. And we're going to make that assumption a bit more explicit in a moment when we look at the work. And so I'll come back to that. But for right now, we're going to say, okay, we'll use sigma is equal to my over I. And so we'll say we're really just dealing with the bending strain energy. Let me give myself a little more room here. Okay, so the bending strain energy is now, we're going to substitute in for sigma. It's going to be 1/2 m squared over EI squared dV. I pulled out the y because that's going to be helpful for us. So hold on, give myself some more room. Oops. Sorry. Oops. Let's do some cleanup here. Okay, let's try that again. So I'm going to separate out what's happening along the curve to what's happening along the cross-sectional area. I'm going to say that I just kind of split that volume integral into an integral along the curve axis and an integral through the thickness. It's actually a double integral through the thickness because you're looking at the cross-sectional area. And the reason why I'm doing that is this might also ring a bell. Does anyone remember what this quantity is? It's like J, it's I. We're in Cartesian, we're in like a not polar framework. So we'll say that, so that this is this, so this quantity, the double integral of y over y squared over a is the second moment of area, going back to probably mechanics of materials stuff again. And so this is actually I. And so therefore, this thing, one of these i's cancels out with one of those i's, and you end up with 1/2 m squared over EI times ds. Now we're almost there. There's one more thing we have to do. We need a constitutive relationship again. We need to talk about how moments relate to bending deformations. And bending deformations are usually characterized by curvatures. What's a curvature? Curvature is it's a measure of how is the slope changing as you march along this curve here. So you can imagine at every point you could draw a tangent line, and you could ask, how is that tangent line changing through my curve? And that's going to be a measure of the curvature of that object. And there's a constitutive law that relates the applied moment to the curvature, and it looks like this. The moment is equal to the curvature at any point along S. Now what that means is that we're not assuming that our curvature is uniform along the arc length, which is definitely a good assumption. We don't think it's uniform, right? I mean, clearly there's like an inflection point where it's curved this way here, and then curved this way, and then curved that way. So kappa is definitely changing as you go along S. So kappa is a function of S. And then this is also multiplied by EI. Awesome, all right. Now what? We substitute that in there. And we get that if we assume that, which is a pretty good assumption, that the material is not changing along S, and that the cross-sectional area is not changing along S, then E and I don't need to be in the integral anymore. We're going to get a squared EI on top of an EI. That's going to lead to a EI over 2 times the integral of kappa squared of S ds. And now, just to make sure that we're matching up what we would normally see in the literature on this stuff, most people for these types of objects don't talk about EI. They usually just lump that into a variable they call B, which is the bending rigidity of the object. And so we'll do that the same just to keep our notation simple. They call this B. All right, and there's one more thing. I've said that the curvature is really kind of describing the change in the tangent along that curve there. So the change in the slope along the curve. Now the slope is demarcated by, let's see if I can draw this. So if we kind of draw our flat line here, the slope at any point S is going to be demarcated by theta at S, which is kind of like, imagine drawing a tangent point and saying, all right, what's the slope of that tangent point related to the horizontal? That's going to be our theta, and theta can change as we go along S. And so if we say that the curvature is equivalent to the change in the slope, then we can take this equation here and write it as B over 2 times the integral of theta prime of S squared ds. And this we're going to need. Okay. This is just a kind of a quick mechanics of materials crash course. I just told you what strain energy is, and then we plugged in a bunch of stuff that we vaguely remember from many years ago and derived what the strain energy in bending of our object is. Why do we do that? Because we want to minimize the Lagrangian to find the governing equations. The Lagrangian is going to be the kinetic energy minus the potential energy. We're saying this thing's not moving, there is no kinetic energy, so all we need to worry about is the potential energy. The potential energy is comprised of strain energy in the object and the work being done on it. So we just found the strain energy in the object. Now we need the work. What's the work? The work, I guess, requires us, it doesn't require us. The work is actually not that trivial to calculate unless we make a particular assumption, and that assumption is that our object is so thin that it's so easy to bend compared to stretching that it's not going to stretch at all. And by stretch, just to be clear, when I use that word, I'm referring to both stretching and compressing. It's kind of like saying bending up or bending down, stretching or compressing. I'm saying this object is so thin that it is not going to stretch or compress. It's only going to bend, which we can reinterpret that phrase as saying we're going to assume that our elastic strip is inextensible. All right, what does that mean? How does that help us? So now we're going to look at the work. And if I redraw my object over here, here's my length L. If this thing is inextensible, then as I buckle this object, my length of my bar is not changing. I've simplified it here, and I'm drawing it as just like a straight line, but it's clearly not a straight line. But it doesn't matter because we're just doing this for geometric reasons. And what I mean by that is, I'm interested in this, what is delta? So if you look over here, I know that my work is going to be P times delta, but I don't know what delta is. And so I need an expression for delta. And delta here is going to be the difference between this point and that point. And if we assume this thing's inextensible, then it's just a rigid bar rotation. And that rotation is going to be given by some angle, theta. And therefore, I can say that, well, just based on some simple geometry, if that length is the same and this angle is theta, then the length down here is going to be L cosine theta. And so then therefore, delta is going to equal my initial length minus just this planar length on that bar there. So it's going to be minus L cosine theta. And we can factor out the L and write this as L times 1 minus cos theta. Remember, why am I doing this? Well, I need to write down the work. Whoa. And the work is going to be equal to the integral over the curve of the force I'm applying times 1 minus cos theta. Where did my L go? Give me a second, let me write this down. Oh, well, where did my L go? Ha, yeah, of course. L will appear once we complete this integral, right? We're kind of splitting this thing up into a bunch of incremental things, and then we're going to integrate along the arc length. And I'm going to make this a little bit more explicit, although I'm still just integrating along S. Really, I'm integrating between 0 and L. I'm going to do that down here, too. And so L will then appear in my work term once I'm able to do this integral. And so what I'm integrating is P times 1 minus cosine theta over the arc length from 0 to L. And now at the end, I would get that my work is kind of PL times that quantity. Okay. So if I come back here to my Lagrangian, then this thing just becomes strain energy to the bending, minus my work, which is going to be equal to the integral from 0 to L of B over 2 times theta prime squared minus P times 1 minus cos theta ds.
Should the signs be flipped because it's negative potential energy?
Yeah, I was just thinking that as I was writing it down, and I don't know if it matters. I think you get the same result, but I'm not sure. So I will try to think about what happened to my signs when you're all working on this, because I was thinking about that exact thing as I was writing it, but I know that what I'm writing is correct from just seeing this in many books and papers over the years. So let me think about that. But yeah, that's a good point. I was thinking about it as I was writing the equation down. So here's what we need to deal with. And here's what we need to minimize. And we could just jump. I want to just point out here, for the sake of full disclosure, this Lagrangian is a function of S, theta, and theta bar. And so we could stick this into our Euler-Lagrange equations and immediately pull out the governing differential equation for this curve. But I don't want you to do that right now. I want you to go through the process of calculating the first variation here. And the purpose of that is, 1, to practice that. 2, because it's going to give us some of the boundary conditions that we can use to solve this problem. So what I'd like you to do, I'm going to split you up into groups. What I'd like you to do is to carry out this minimization. So add an epsilon eta or an epsilon theta squiggle, or however you want to do it, and epsilon theta or eta prime to your theta prime, and then carry out this integration by parts, arrive at the first variation in the total potential energy. And you should be able to identify both the governing equation and some of the natural boundary conditions on this structure. I will split you off into groups and then just kind of check in on you every so often. The last thing I'd like you to do is, once you solve this problem, is try to think if you can understand the boundary conditions you found in terms of the boundary conditions that you recall from mechanics of materials for the equation of an elastic curve. Remember, you often solve these things with two kind of generic examples, one being simply supported conditions and one being doubly clamped boundary conditions. So I would like you to go through the process of calculating the math, but then also thinking conceptually about, what am I talking about when I say that these boundary conditions exist or fall out of this calculation? So with that, I'm going to, unless there's any questions in the moment, I'm going to split you off into breakout groups and have you start calculating this thing out and see if we can practice our variational skills and identify the equation of the elastic curve.
We're looking for the equation that
Minimizes that energy.
and would describe the curve.
No, you're looking for the governing differential equation that we would, if we could solve it, would tell us the shape of the curve. But so remember, the result of this calculus variation is not the answer; it's the differential equation that we then solve to get the answer. It's what is the governing equation. Okay, let me break out over here. Create.
We can't, I think you're muted, Doug.
It keeps muting me. Thank you. I don't know why it does that. Let me see here. Am I muted? Yeah, there we go. All right. All right. Hopefully you found that the governing equation for the Elastica is theta double prime plus, let's say, P over B times sine theta of S equals 0. Oftentimes you'll see this thing defined as lambda in the literature. Kind of remarkable that this exact same equation is the equation that describes the oscillation of a pendulum, which is an initial value problem. But in the case where you return it from an initial value problem to a boundary value problem, the exact same equation describes the shape of an elastic curve. Perhaps even more remarkable, we're not going to do this, but the equation for, this is a planar elastic curve. So this is only going to describe stuff happening in the void. If you wanted to get the equation for elastic curve in 3D space, so like a twisted rod that could be bending and twisting and everything, you get a much more complicated equation that also happens to be the mathematically equivalent form of the equation that describes a spinning top. These are, I don't know, this just kind of blows my mind when I think about it. What's that? So the equation that describes the motion of a spinning top is the same equation that describes the shape of a elastic rod in 3D. So like right now we solve for a 2D problem. Whoa, there we go. 2D problem. Pretend there's no width of this thing. So it'll just tell you this shape, and it'll do, actually this equation will do even like this shape. If you could imagine that this shape was projected onto the board. But the actual equation of something like this, like the 3D shape, the equation that describes this, is the same equation that describes the spinning of a top. So I don't know. There's nothing to say about that other than that's kind of remarkable. I feel like I should be pointed out. Okay, so this part you could have gotten immediately from just inserting this into the euler-lagrange equations. What you also probably found is something that looks like B theta prime times eta evaluated from 0 to L equals 0. Oh, that's not 0. Equals 0. These are your boundary terms. And what I was hoping you would be able to pick up on is how does this relate to what we kind of know about the boundary conditions on an elastic bar? And what we know, if you think about things in terms of simple support, what does a simple support boundary condition mean? It means that the angle could be any arbitrary value at the end there. The angle at the end of the beam can be any arbitrary value. And the only way the angle at the end of the beam can be any arbitrary value is if there's no moment acting on that beam, resisting the rotation of that end of the beam. And look, here's what we have. We have an equation here that says the product of this thing times this thing has to be 0. And so what does that tell us? It tells us that one option is that this quantity could be 0. What does that mean if that quantity is 0? Well, that quantity is theta prime, which is equal to kappa. Actually, let me write this out a little more clearly. That quantity is equal to theta prime at L, which is also the same as kappa at L, which is also the same as what you probably learned in mechanics of materials, which is approximately equal to the second derivative of your deflection at that point. no curvature, that's a simple support at that boundary. We could do that same thing at the other point. We could say that also, this equation could tell us that the curvature at the other end of the boundary is equal to 0. We derive these boundary conditions by minimizing the functional for this curve. These ones are not that hard to kind of imagine and visualize, but they just dropped out of the equation for us. They're exactly what we see. These are what's referred to as the natural or static boundary conditions. That's not it. And the important thing I want you to take away from this is when you use a variational procedure to derive the governing equations, you get the governing equations and the natural boundary conditions. What you don't get are the essential or kinematic boundary conditions. I say these are natural or static because think about what this means. Static kind of implies that we have something that has to do with equilibrium. Something relating to our the constitutive relationship between forces and deformation. And in this case, it's really between moments and curvature. What we don't get are the forget this term, essential or kinematic boundary conditions. What are the essential or kinematic boundary conditions that we don't get? So for an elastic beam that's sitting on supports, give me something. Can you let me think of what the kinematic boundary conditions are? So ones that are prescribing geometry. Essential meaning they well, I guess if I define that, it'll give away the answer. What are the boundary conditions we don't get in this procedure? Well, for the sake of time, I will just tell you the answer, which is that we don't get something that specifies deflections on the curve. We don't get the fact that we might need to say that the deflection at L and the deflection at zero are equal to 0. So we get these for free just by doing the calculation of variations. One of the things I don't get a chance to show you, but if you end up going through the deriving the euler-lagrange equations for when you have one independent variable, so like say x, and then u prime and u double prime, the one I wrote on the board last class, you'll find that the natural boundary conditions in that case are not trivial. They are quite complicated, and they're not necessarily ones that you would write down just by kind of looking at the problem and solving it. This is always true. You always get the natural or static boundary conditions from the calculus of variations, and you're left having to discern only the essential or kinematic ones. We're out of time, and so I will see you all next week. I hope you have a nice weekend. Thanks, everyone.